Всем добрый вечер. Спасибо за приглашение. Thank you for inviting me here. I'm very pleased to be here and to see your amazing office and to give a talk on what I was doing as part of my PhD and probably should develop further. So what I'm going to present is quite a small part of the PhD thesis, but I think it's quite important. It might have been probably developed better than it is. So I will start with introducing myself. So I graduated from the Novosibirsk State University from the Mechanics and Mathematical Department in 2008. Then I worked in the industry for several years, and then I went to study in Carnegie Mellon University as the beginning of joining Innopolis University. It was the, so to say, precondition for joining it as an employee. So I graduated from the MS-ITSC master program, and then I joined as a researcher in Innopolis University, and at the same time as a PhD student of Professor Bertrand Meyer, and I defended my PhD in 2019 in the Computer Science Research Institute of Toulouse under his joint supervision together with Professor Jean-Michel Bruel. And the topic was seamless object-oriented requirements. Because we're short of time, I'm not explaining the details what hides behind this title, but I'm going to present a subset of it. So my current research interests being, if we specify them in the simplest way possible, I'm working on methods for constructing reliable software from unreliable requirements. So how do we define secure software? So when we just start working on software security, we may associate it with some specific problems like stack or buffer overruns, SQL injections, something very specific. And as we proceed, as we progress, we develop, we generalize our understanding. So, for example, we may say that it shouldn't be vulnerable to anything from the OWASP top 10 list, which concerns only web applications. And then we can generalize it further, saying that it shouldn't be vulnerable to anything from the global list of vulnerabilities specified on the mitra.org website, and then we can say that it ensures integrity, confidentiality, availability, accountability, the sub-properties of security that we can find on any textbook on security and software requirements and software engineering. And then we will end up in the simplest way of defining it. We can say that the software is secure if it has no undocumented functionality, whatever it means. And so we will develop this understanding with the experience. But what does it mean formally? Like, what does it mean that the software has no undocumented functionality? So first of all, we can infer some immediate observations from this property. First, the security is a function of functional requirements, because it is when the software has no undocumented functionality. So this means that security is a function of functionality, so to say. And the functional requirements should be complete and consistent, because if they are not complete, then we cannot say that the software has no undocumented functionality, because we have not documented the functionality exhaustively. Then we have to at least document it completely so that we can assert that the software features nothing undocumented. So, of course, once the requirements are documented, the code should correctly implement these requirements, and maybe even more importantly, it must not implement anything else other than these requirements. This is what basically defines security. Okay, so this all looks quite convincing and simple, but how does that help the developers? So the question is, if you are a software developer whose daily routine is writing code, how does it help you? So what can you do to make sure that you are not writing something that is undocumented and that you are writing something that is correct with respect to the requirements which are documented? So and we're going to focus on this question in this talk, and I guess many of you know what is Hoare logic. It's a formalism, mathematical formalism to reason about programs' correctness. It was introduced back in 1969 by Tony Hoare, and expressions like statements, better say formulas, in this logic take the form that you can see on this slide, where P is a precondition, R is the postcondition, and Q is the program that has to guarantee the postcondition given the precondition. And it also has some axioms. The most probably important one is the axiom of assignment. It says that if P holds, assuming that we replace all free occurrences of X with expression E, and if we assign E to X, then P will hold in the end. So this, I'm saying that this is probably the most important axiom because it does not hold in, for example, in object-oriented programming in its pure form, because of, so first of all, because of aliasing and possible circular dependencies, and well, many effects that are derived from the possibility of aliasing. Then we have some more complicated axioms. For example, the two of them are very similar. So the second one is called the postcondition strengthening. It says that if from a postcondition R is stronger than some statement S, then we can replace R with S, and this the initial theorem will still be derivable. It will hold. The third axiom is called precondition weakening. It says that if some statement S is weaker than the initial precondition P, then we can replace P with S, and the resulting theorem will still hold. And the fourth axiom, it's not axiom, it's an inference rule. So it says it's a rule of consequence. It says that well, it basically allows you to connect statements in one program with the statements from the second program in sequence. Then the final rule is the rule of iteration. It says that if some condition P is preserved between between the precondition and postcondition, so if we can prove that it holds, if it holds in the beginning, then it also holds in the end, then we can say that well, this condition is it can be used as the precondition of a loop with the exit condition not B, and the post condition will be not B and S, where yeah, I think it's a typo here. It should be not B and P. Yeah, and P becomes the loop invariant here. So in the post condition on the rightmost side, it has no pointer. Okay, so you should replace S with the P. Okay, so and then the next step was to introduce this logic at the level of actual development. So this is a picture of the Eiffel Studio IDE, where you can see it's a fragment of the development process. So when you hit dot after some variable, you typically have a list of features that you can apply to this target variable, target object. And this is the case for almost any IDE on the market, and the difference of IDEs based on design by contract, although I know none of them except Eiffel Studio, so you can see the contract of each feature. So you can see the precondition that you have to meet as the caller to in order to use this feature, and the post condition that this feature will guarantee you in exchange. So the next step was to create a tool that can statically prove correctness of implementations with respect to contracts. So the tool is called Autoproof. It was initially developed by Julian Chen and the former students, or the former PhD student of Bertrand Meyer, and this tool can either find a proof to accept your program, so to say, as a proof of the theorem with the given precondition and postcondition, or it may fail to find to accept it as a proof, but it doesn't mean that your program is necessarily incorrect. It just means that the tool was unable to find to discharge the proof, basically. So yeah, the tool is sound, but it's not complete. Okay, so how can we take advantage of all this stuff when reasoning about security at the level of code? So there is a notion of well-definedness. It exists. It has long existed in math, and it defines well-defined expressions are as expressions that yield the same unique interpretation or value. Otherwise, the expression is said to be not well-formed or ill-defined or ambiguous. So, for instance, if a function takes real numbers as input and it yields different results depending on the actual notation of the input, then it's not well defined, and basically it's not a function at all. And I decided to apply this notation at the level of contracts for coding, and as applied to contracts, a well-defined contract, if its definition allows for a unique set of side effects regardless of the chosen implementation. So in other words, if you have a well-defined contract for a feature, regardless of the code that you write to meet this contract, this code will have the same set of side effects. and any deviation from it, from this set of side effects, will force the prover to reject the program. So as a corollary, well-defined contracts disallow undocumented functionality and thus ensure security of the code, meaning that you cannot just mistakenly write something that the prover will accept, but will result in something desirable. Okay, so let's take a specific example. So this is an implementation from a library that I will discuss in more detail later. So this feature copies the contents from an object which is a two-dimensional array. It is passed as an argument to this function, and it copies the contents of this object into the current object. So it's implemented inside the 2D array class, and its postcondition says that the matrix representation of the current object has to be model equal to that of the other object. And model equality is a separate notion. It was created for specifically to make programs verifiable with Autoproof. I'm not digging into the details of model equality, but this is how the postcondition looks like. And so what do you think is the problem with this contract and this implementation?
It maybe do nothing if condition is false, it does nothing.
Right. So if the two objects are aliased, if the other object is aliased with the current object, then it does nothing, and this implementation is correct with respect to this postcondition. But is it the only implementation that the prover will accept? What can we? I have intentionally left this space here. So can we add anything harmful here that will still be accepted by the prover? So you're on the right path. It doesn't handle the aliasing situation. Okay, so what we can do is we can add else to this if statement and basically wipe out the array, which will result in an empty array. So it will erase all the data from it, and the postcondition will still hold because the other object is aliased with the current one, and of course they are model equal because they are the same objects. So how can we avoid this situation? So remember that postconditions are statements over two states, the pre-state and the post-state. So how can we fix this possibly? Okay, so we can add the old keyword which refers to the pre-state of this of the expression on the right, and in this case we will explicitly say that the matrix representation of the current array in the post-state model equals to that of the other object in the pre-state, which assumes that we refer to the initial state of the object from which we copy the data. Okay, so in this case the prover will reject this malicious implementation, but the question is, how do we detect such contracts? How do we detect such not well-defined contracts? And the answer comes from math, which basically, so what this routine is saying is that, so this is for another data type, it's for stack, just to have different examples. What we are trying to prove here is that the contract of the push operation, of the push feature, is well defined enough, it's strong enough to guarantee that the stack objects like find themselves in the same equivalence classes. So in other words, if two stacks are equal in the beginning, in the pre-state, and assuming we modify nothing else other than these two objects, then if we apply the push operation on these two objects, then they will remain equivalent in the post-state. So, and the prover has to accept this theorem formally. It has to statically prove it. And in order to do that, the prover looks at the contract of the push operation of the invariant of the stack class and at the contract of the definition of the equality. Okay, so big deal. Let's just say that two stacks are always equal. Let's say equal always, the equality definition always returns true. So then we have to make sure that this is not the case. And in order to fix this, to avoid this problem, we have to assert that if two stacks are equal, according to the definition of equality, then their observer methods are also equal. So if we define equality as always being true, then we cannot infer anything from true, because true is the weakest statement. And so if we want to have observer methods like item or more well known as top and checking for emptiness, then we will have to make our equality strong enough to infer equivalence of these observer methods from it. And so yes, and then we submit this auxiliary method to Autoproof. So I want to pay attention to this trick. So this method called stack observers well defined, it's not used anywhere. I mean, we never call it, we just arrange a separate class where we enumerate these auxiliary methods, and these methods are basically theorems, and it's the presence of the static prover that lets us do this. We can write code that is not supposed to be ever executed, it just expresses some theorems. And yeah, what's next? So yeah, I applied this method to Eiffel-based 2, which is a fully verified container library. It's a result of another PhD thesis. You cannot see the name. It's a result of Nadia Polikarpova. It's another former PhD student of Bertrand. And the code that I have shown to you previously is from this library. The class is yeah, it's here, array2. It's two-dimensional array. So and the result was that after applying this method, I identified that so Autoproof failed to prove to check well-definedness of 8 implementations of the copy feature out of 17. I didn't go yet into developing an actual exploit for each of these problems, because it was not the main focus of my PhD, but as I said, I should probably develop this direction further, because I think it's there is something probably quite important here. And happy Mathematicians Day. It's the 1st of April, so at least in my alma mater in my first university, this is a good enough reason to cancel classes in the mathematical department. So, questions?
So did you understand how it works?
I'm not sure exactly, because of many notations are introduced very.
The language we don't understand now.
Okay, let's discuss the specific.
Maybe we can talk about practical applications for developers in real life. How usual developer can use it.
We will define use case.
So these statements should be generated. Because they all look similar. They should be generated automatically by the tool, which is not the case yet. And so first of all, the developer should use this tool or a similar one, because there are lots of experimental provers that work around the same principles, and the problem is that they are not used yet in practice in the industry. So, and if they are used, this would probably provide more feedback to improve these tools. So, and another problem is that developers mainly do not write contracts. So, it's a serious problem, I would say, in the sense that it's not that simple. You cannot just say, "Hey, start writing contracts today." It doesn't work like that. So it's a matter of introducing some changes to the development processes, and actually, even if there is lots of legacy code without contracts, it's actually possible to introduce additional classes that become clients of this legacy code, and we can define contracts at a little bit higher level of abstraction. We do not define them right where the code is implemented, like here, but instead we introduce like auxiliary routines like this one, where we in the body of this routine we call the method that we want to provide the contract with, like the copy, and then we say what contract this method has to satisfy, and then we will need to change a little bit the verification logic, but I think it's doable in practice.
And contract, you mean the P and Q notation you define? Yes.
Yeah. So, well, this is the roots of the scientific root of the contracts. It's
okay. And this tool, is it general purpose for developers who do coding, maybe Android applications and websites, or it's maybe more suitable for those who are writing some critical software, for example? Who are first users of this tool?
In principle, anyone who practices object-oriented programming and is ready, who are ready to write contracts. Actually, we are working quite slowly right now, but there is a willingness to improve, to simplify the use of this tool, because its usability is far from perfect, but this effort requires some dedicated resources, dedicated focus, and the task is not simple. So there is a small project in Innopolis University in which I am participating. It's focused on basically matching natural language specifications with the formal specifications. So we're trying to remove the need to write formal specifications manually, because developers are not doing it, and there is a good chance that they're not going to do it ever. And now we have machine learning developing at high speeds, so maybe we can take advantage of this. Actually, there is a prototype already in this project. It's quite primitive, but it can serve as a proof of concept that this task is doable. So yeah.
Can we see at these contracts as a test cases?
Yes, basically they are test cases, but in a more abstract and formal, expressed in more abstract and formal way. And actually, yeah, I forgot to mention it, there is another idea to unify use cases and writing contracts. So we have just started working on it, but we noticed that it should be possible to map use cases into auxiliary routines of this form and then submit them to the prover. And so yeah, it requires basically another portion of tool support, but yeah, we are working on it, and the problem is there is not much time in a day to work like on this and that. We don't have that much resources yet to develop this like ideas very much. Yeah.
The next my question is, which kind of rules the contract language support right now, and maybe you'd like to see in future?
It's very flexible, I would say.
Maybe some practical examples which I saw some comparison, equality check, yes, and maybe there are some other interesting.
Well, the language is very expressive. You can basically write down any. I don't have examples on my slides, other than I have shown already. So you can capture any statement in the first order predicate logic. So this is what I can say about expressiveness of this language. So you can use it to specify any program behavior that you would like to. At least we could not find any example of software, or a piece of software with a certain behavior that would not be specifiable with the language of contracts.
Okay, and is this a static analysis or dynamic analysis?
For this presentation, it's static analysis, but of course, well, contracts are basically assertions. Contracts, the contract sublanguage of a programming language, it's a syntactic sugar. You can write just assert statements. In the beginning, they will map to preconditions, and in the end of your method, it will be postconditions.
Okay. And if it's static, then how you can understand that how you can understand that you reach some property of the program in general? You know, it's not possible. For example, you know that you input one value, and you do not have a general way to understand what the output will be.
You can still run tests.
But it will be dynamic analysis.
I mean, nobody said you have to use only one. So you can still. This is still code, and you can still run your tests if you want. If you want more tangible evidence of correctness, so I would even say you should. I mean, you shouldn't just trust the prover because sometimes it doesn't accept something that is correct. You know that the code is correct, but the tool is not precise enough to accept the correctness. And in this case, you will have to convince yourself using testing. So, of course, they have to complement each other. Also, there is an ongoing work. There is a new PhD student of Bertrand. She is from China. She is working on actually a tool set that would combine these two approaches. And basically, she wants to produce something like, so for example, if the prover rejects your code, it not only rejects the code, it produces a counterexample. So if it says no, the code is incorrect, then it produces a counterexample using which you can see that indeed this counterexample leads to a violation of some property.
Okay.
So
another question: you at the beginning of the presentation you said that you have to check that program doesn't implement that is not required. But as I understand, using these contracts, you can mostly, as I understand, you can check only how to check what's already written and in specification and what's actually how you can understand that program do not do.
Yeah. So let's look, for example, at this slide. You have the functional specification of this method copy. It describes what the method is supposed to do, and it does what it's supposed to do because the prover accepts it. But we can say that this contract is not secure. It's not well defined. It's not strong enough. Well, in this form, it's already strong enough. So because we have already fixed it, but without the old keyword.
I can add in this function some code that going to web and doing something, calling some API, and this condition at the end also will be true.
Yes. So I forgot to say an important thing. So all provers they need so-called frame conditions. They need specification of what is allowed to be modified, and by default, these are objects explicitly mentioned in the contract. So in this case, the prover will assume that the frame condition consists of the matrix representation, model field, model attribute, and the other dot matrix model attribute, and it will not accept modification of anything else. So this is something you can see it explicitly here. There is a modify statement.
Oh, yes, my question was about what this.
Yes, it was a little bit of cheating not to mention it explicitly, but this is something that actual provers need for verification, because you have to limit the side effects. If you don't do that, then the second call in your program may cancel the effects of the previous call. So and that's why we have to limit at the level of specification what the method is supposed legally to modify.
And what happened if I wrote the line modify and I specify a frame that stack 1 and stack 2 have to be checked, but what will happen if I will?
Okay, let's go back and understand. Yes, so let's go back to the implementation method. So let's say you in the beginning you say explicitly that this method is allowed to modify something, but then you will have to specify these effects in the postcondition, because if you do not specify these effects, if you leave the question open how exactly you modify these objects, then you will fail this check, because the prover will not be able to assert that if two objects were equal in the beginning, then they will remain equal in the end after this well, after the same call is applied to these both objects, because the frame will be so here you will have to provide more objects, and they will increase the level of uncertainty, and this mechanism, this method will force you to go back to this method, to the implementation method, and strengthen its postcondition. It will force you to specify how exactly you are going to modify this, whatever you have specified in the frame condition, and then it becomes your functional specification. And then if it's visible at the level of postcondition, then you cannot hide anymore that you are doing something. Well, you are doing something, and the clients of this method will also see these effects at the level of, well, in the moment the developer attempts to call this method. So yeah, like here, you see, you can see everything, the description of the side effects. Thank you for your questions, because I thought this presentation is very, very simple. Now I understand that I still have some blind spots. I mean, I assume that something will be easy to understand, but I mean, I have to explain even better the details. I hope you found it interesting. I always try to stay at the level of code, both in my papers and slides. So
thank you very much.
Thank you.